So we've been talking carbohydrates here. So remember, carbohydrates are referred to as sort of simple sugars, and they're basically made up of carbons, hydrogens, and oxygens. And we talked about some of the structures of carbohydrates, sort of the straight chain structures of carbohydrates. They basically will have one of two sort of organic groups up on top. That is going to be either really our aldehyde group that we saw in organic chemistry, which will be sort of at the top, or they will also have perhaps a ketone sort of group here, as really it's a functional group here of each of these sort of carbohydrates. And if it does have really the aldehyde group up on top, we do refer to it as an aldose. And if it has the ketone group up there on top or near the top, is what is referred to as a ketose, because obviously it has a ketone group. Just like in organic chemistry, as we talked about, sort of the situation where you'll find these groups located is pretty much the same position as they are in organic compounds. The aldehyde group, again, because it has that hydrogen at the end, will pretty much always be at the top there. The carbonyl group there, the carbon-oxygen double bond. The ketone, because just like in organic chemistry, it does need a 3-carbon sort of run with the double bond in the middle. You always find that carbonyl or double bonded carbon, basically one in from the top because of that, because it cannot be obviously at the end there because it needs that sort of 3-carbon run. We can draw carbohydrates, and very commonly sort of drawn in this sort of fashion here. Sort of like a line structure, if you will. Once again, where each of these sort of lines intersect, those are carbons that are present. And so there would be a carbon here, a carbon here, a carbon here, and a carbon here. They also usually will have some OH groups or hydroxyl groups and some hydrogens along the way here. It might have something like this, maybe. And we could also classify these carbohydrates in addition to the sort of functional group that they have up on top. We could also classify it by the number of carbons that they have. This particular one, we do count all the carbons present here. So 1, 2, 3, 4, 5, and 6 carbons. So that would be a hexose. There's a tetrose, which is 4 carbons, right? Pentose, which is 5 carbons. Hexose, which is 6 carbons. So that's another sort of classification that we could have when we look at these carbohydrates. Now, in addition to that, we also talked about the idea of a chiral molecule and a chiral carbon. And when we do have a chiral carbon or a molecule that is chiral, that means that when you take the mirror image, it is non-superimposable on the original structure. So the way that we could kind of recognize, for example, that a carbon is a chiral carbon is basically that carbon should have 4 different groups attached. And that is how you will know it is really a chiral carbon. Achiral, by the way, means that it does have a mirror image that can be superimposed on the original structure. I wrote super impossible there. So it could be super impossible as well, but superimpose maybe. It can be superimposed on the original structure, which could be super impossible maybe. And basically, to kind of determine if something is an achiral carbon, you would probably find two groups that are the same on that carbon, and that would mean that it doesn't have obviously four different groups that are attached. So when we talk about mirror images that are non-superimposable, again, the classic example, like we talked about, I think last time, is the hand. So again, if you put your hand up to the mirror, you get your other hand. And if you take your other hand, which is the mirror image, out of the mirror, you can do as much twisting, moving as you want. You'll never be able to get it to sit perfectly on your other hand. There's always will be something that's sort of wrong. Like again, we're palms down, but our thumbs are on the wrong side. We flip it over. Thumbs are on the right side, but palms up, palms down. So it will never fit exactly perfect. And that's what it means when we take a chiral compound and we take its mirror image, it won't fit even if you try to rotate it. And that's different than an achiral compound, where again, if you do sufficient rotation, you will get it to sort of lay perfectly on the original structure there. Now, let's see here. There's that. We also talked about the idea as well that you can have more than one chiral carbon in a carbohydrate. So we also can have a D or L, I think we also talked about, sort of orientation. D means right, L means left. And in terms of carbohydrates, what we're talking about is the last chiral carbon on the chain there. And that should be the one that's furthest away from the organic group there, the aldehyde group or the ketone group, the carbonyl group really. And if that OH is on the right, then it's a D, and if it's on the left, it's an L. So in the one I drew here, this would be our last chiral carbon. As I also mentioned, usually not 100% of the time, but most of the time, you'll probably find your last chiral carbon hanging out right above that last group there, or the last carbon. And that's going to be a D in this case, as it is on the right-hand side that we have here. Any questions on any of that stuff there? I vaguely remember we talked about it. I think that was before Thanksgiving, maybe. I don't know. I think that's what we did. All right. So at the very end last time, we started talking about sort of putting these guys into a ring sort of structure and what happens when they sort of close up on each other. And these sort of straight chain sort of guys like we have here can close up on each other. And as we talked about there towards the end, they will make these cyclic structures. And these cyclic structures essentially will look very similar to our kind of cycloalkanes that we saw. And they usually will look, as we saw there at the end last time, as really one of these two sort of structures. And they do look very much like a cyclohexane and a cyclopentane type structure. But again, the importance here is as it's incorporating and sort of closing in on each other to make this ring structure or the cyclic structure, an oxygen does get incorporated into the ring. So we actually have one less carbon than in a cyclohexane or a cyclopentane. So this particular ring here has only 1, 2, 3, 4, and 5. Once again, we do have our oxygen that's sort of been inserted into the ring. And again, that happens as basically those carbons kind of close in on each other. Oxygen double bond and an OH group sort of move around a little bit, and that oxygen gets incorporated in there. This guy here, again, going to make a 4-carbon ring with that 5th spot there basically occupied by the oxygen here in this case. So when these guys do sort of form these cyclic structures from sort of that straight chain that we were just looking at there a second ago, they will pretty much form one of these two sort of rings. And we could really figure out sort of which ring it's going to form by, how it comes together to make these cyclic structures. So if we look at just an example again, and we'll walk through this one more time here, how to kind of turn it into a cyclic structure. So if we have this carbohydrate here, We'll just do maybe OH here. We'll do OH here, OH here, OH here. Okay, so if we were again going to want to draw this guy into that cyclic structure, the first thing we really want to do is you might want to label the carbons. And remember, much like in organic chemistry, that functional group is really the lowest number carbon. So where we have the carbon-oxygen double bond should have the smaller number. So this really should be carbon number 1. Remember, there is a carbon right there at that intersection, which is carbon number 2. There's a carbon right there, which is carbon number 3 at the next intersection, carbon number 4 and 5 at those intersections. And let us not forget our friend there, carbon number 6 on the bottom in this case. So one of the ideas of how to kind of turn this into a cyclic type structure is we're basically just going to take this guy and pretty much just drop it on its side. So we're just going to take it the way it's standing and just tip it over to the right there. And when we do kind of tip it over to the right, if we sure to redraw this, we would end up with something like this. And again, renumbering, starting at our same part, which is number 1, number 2, number 3, number 4, number 5, and number 6 there. We can now place really our remaining groups up there. Remember that if we do drop this guy basically straight on his side there on the right, pretty much everything on the right-hand side here is going to end up on the downward side. And everything on the left-hand side will then end up above it or up, right? So everything on the left here will basically end up. So if we do that at carbon number 2 here, we have our OH there. Carbon number 3, we have our OH down, H, and now OH would be up here, OH up here, H, and H. Any questions on that so far? So in this case, where we have really a hexose like this, a 6-carbon sort of setup, what's going to happen when this thing comes to sort of close in to make a ring type structure is it's always going to be carbon number 5. That is essentially going to kind of do that process. And in this case of the hexose, it's really that last chirocarbon, which in this case is number 5. It's going to actually go and attack the carbon-oxygen double bond. So wherever that carbon-oxygen double bond is located, which means this guy is going to come and basically attack this carbon right here. So once you sort of arrange it like this, you can really figure out right off the bat what size ring that you need to draw for this, either that sort of 5-carbon ring or that 4-carbon ring, by frankly just circling the carbons that are involved in what you just did. So clearly this carbon's involved, this one's in there, that one's in there, and that one's in there. So if we just count the circles there, there's basically 5 carbons that are going to then kind of incorporate into the ring as that 5 and that 1 sort of closes up on each other. So from that point, you could really just draw that 5-member ring, which once again looks like that cyclohexane ring, but again, it does have that oxygen incorporated into the ring. Now, what always happens when these things sort of incorporate into a cyclic structure is, as you could kind of see, there's usually something that's like left behind or out of the ring. And in this case, which is very common, is our carbon number 6 there that's pretty much out of the ring. It's not going to incorporate itself into the ring. So where carbon number 6 ends up is always the top left there to the left of the oxygen. So that is where that carbon will always end up. So he will end up right about here. And that is our CH2OH. And again, that's going to be our carbon number 6. And that's about pretty much the position where carbon number 6 will pretty much always end up. Question on that there. Now, that's really important because now we're going to use really carbon number 6 as a reference point of how to number all the other carbons. So we're going to actually go counterclockwise here. So that's carbon number 6, which means the one it's connected to would be carbon number 5. And again, going counterclockwise, that would make that carbon number 4. That would make that carbon number 3. If I learned how to count backwards, that would be 3. That would be 2. And then that would be carbon number 1 there. So again, we always put that carbon number 6 up and to the left. And then we kind of use that as a reference to sort of number all the rest of the carbons that are present. Any questions on that so far? All right, so what is left at this point is pretty much just to put what's on our picture. So we always will pretty much skip carbon number 5 in this situation when you have a hexose, because carbon number 5 and carbon number 1 frankly come together and are joined right there. So that's where those guys come together. That's also where, you know, these oxygen gets incorporated into the ring as it's closing in. So we kind of skip number 5. So then we go to the next one, which is carbon number 4, which is this carbon right here. And what we're looking at is really, where's the OH? And we can see that the OH in this case is up. So when we go to our ring, we would draw a line and we would put our OH group up. We would then go to carbon number 3, which is next door. And we see that the OH group on carbon number 3 is down, which means we go to carbon number 3 and we draw our OH group down in this case. We would then go to carbon number 2. And we see our OH group here is down as well, which means we would then draw an OH group coming on the downward cycle here. Any questions on that there? Now, very common in these sort of cyclic structures of carbohydrates, there is something at the other end of that line, which is the hydrogen, but it's usually not incorporated there because it gets a little crowded if you start writing the hydrogens, and there's a lot of stuff on there. But on the other end of the OH group is the hydrogens that we see here. But again, when you write them in the cyclic sort of form, we oftentimes will leave the hydrogen off so it doesn't get so crowded. Now, the very last one, which is our first carbon there, that is determined by what is referred to as the anomer that you want to draw. And it may be the alpha or the beta anomer. And if it's the alpha anomer, it means that the last OH group will go on in the downward position. If it's the beta version, it means that last OH group will go up. So for example, here, if we were to draw the alpha anomer of this guy, we would draw that last OH in the downward position. And if we wanted to draw the beta, we would have drew that last OH in the upwards position. Everything else would be identical. So we would still have our exact identical setup here. And we would just draw our last one in the upwards position if it was a beta anomer that you're drawing. So they typically will tell you, obviously, to draw the alpha or the beta, and that's how you know sort of what you should do with that last carbon in that last OH group that goes there. Any questions on that there? So again, drop it on its side. If you don't really want to drop it on the side or rewrite it, you could just remember everybody on the right ends up down, everybody on the left ends up, so you can leave it upright if you want. And again, figure out how many carbons will make up the ring. Start with the ring, put that kind of last guy over there on the left, and then work your way backwards. Any questions on that one there? All right, so since you're professionals, let's do one more here. I think you're professionals, maybe. There you go. All right, we'll just do this one. All right, so why don't you draw the let's do this here, maybe. Yeah, let's do this guy. And we'll do UOH, OH. All right, why don't you draw the beta anomer of it in the cyclic structure? Okay, let's take a look. So once again here, we want to start maybe numbering. Should start out our functional group there. 1, 2, 3, 4, 5, and 6 here. Again, what you could do is basically just kind of drop it on its side. And once again, as we talked about, 2, 3, 4, 5, and 6 here. Everybody pretty much on the right will end up down, and everybody on the left there will end up upwards, or you could just remember that and not drop it on the side. This renumbering here, 1, 2, 3, 4, 5, and 6. That means here carbon number 2, my OH is going to end up up. 3 is going to end up up. 4 is also going to end up up, and 5 is going to end up down. So once again, we're looking really for that sort of last chiral carbon from our functional group there. And in this case of our hexose, it is carbon number 5. Once again, is going to be our guy that's going to close in. It's going to again go and attack our carbon oxygen double bond. Once again, we can just circle the carbons involved, 1, 2, 3, 4, and 5. So again, we're going to start with that 5-member ring that has the oxygen incorporated in there. As always here, our carbon number 6 is left out of the fold here. So we're going to put it up into the left there of our oxygen. And that will give us, again, our reference point for carbon number 6, which means, again, if we go counterclockwise, 5, 4, 3, 2, and 1. Once again, we're going to skip over carbon number 5, as that is pretty much this area here where it all kind of gets incorporated into the ring. So we'll go to carbon number 4, where our OH group is up. Carbon number 3, our OH group is also up. And carbon number 2, our OH group is up in my made up example here. And now the last one here, which is the beta, will end up in the upwards position in this case. Yeah. Any questions on that there? All right, let's try one more here, and just to see, let's do something. Let's see. Let's do that. Let's do that. Do this. Do a little bit of that, a little bit of that. All right, why don't you draw the alpha of this one here? Okay, so let's take a look. This one's a little bit different. It is a ketose, right? We have our ketone group right there. Right, we're going to roll our carbons out. There's a carbon, obviously, where the double bonded oxygen is hanging out. So we would still number it the same way. We want to give that group the smallest number, but it actually will be carbon number 2 in this case, right? As we got to start at the top there. Can't start in the middle and go backwards or anything like that. So that still gives that group the smallest number possible. That would be carbon 3, carbon 4, carbon 5, and carbon 6 here. So you're still going to approach it the same way. If you want, you're going to drop it on its side, or again, remember, everybody on the right goes down, everybody on the left goes up. If we did drop it on its side here, we would have this here. We would have a little bit of that right there. And then we would have this at the end here. And again, numbering, that would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 in this case. Again, everybody on the right-hand side is going to end up down, which means at carbon number 3, my OH group should be down, my hydrogen should be down there, and my OH group should be down there. And again, everybody on the left will end up on the up side there. And going that way would mean hydrogen, OH, and H in this case. Yeah. Questions on that so far? Yeah. It really doesn't matter. Yeah. So because we're going to put it into the cyclic structure anyways, it's going to go away, basically, that double bonded oxygen. Other questions? So in this case, we're still going to look at carbon number 5 here, which is sort of our last chirocarbon down the road. And it's going to close up the ring similar to what we saw before, except in this case, it wants to go to the carbon-oxygen double bond. So it's not going to go to carbon 1 in this case. It's going to actually only go to carbon number 2 because that's basically what makes that oxygen, all that getting inserted there into the ring structure. So it always will end up at the carbon-oxygen double bond. In the case here of our ketone group, our ketose, we actually will end up there at carbon number 2 rather than carbon number 1. That does affect the size of a ring that we're going to basically build here, because that now means we have 1 carbon, 2 carbons, 3 carbons, and 4 carbons only. So we do want to use the 4 carbon looking chain, which again looks like cyclopentane, but not with an oxygen inserted in there. Now, the orientation of where we should start with this is still the same. That last carbon, which is not the chirocarbon, which is carbon number 6 in this case, will still end up to the left of the oxygen as CH2OH, and that's carbon number 6. So now we could still number our ring like we've done previously, and that would get us carbon number 5 here, carbon number 4, carbon number 3, and carbon number 2 in this case. Yeah. So when we close this thing in as a ring, we do end up with actually not one thing that's out of the ring, but we actually end up with another carbon that is not part of the ring, right? And in case you're curious, that's where carbon number 1 is. There is not incorporated into the ring. It's actually off of the ring, as we can see there with our arrow. So we're going to kind of finish it just like we normally would. So once again, we're going to skip that 5th carbon that sort of makes the ring come together. We're going to go to the 4th carbon there, and our OH group is upward here. Our 2nd carbon, our 3rd carbon, our OH group is downward. And now our last OH group, because it's alpha, should actually end up at our 2nd carbon going downward. And that means that the last carbon that is not part of the ring actually will end up on the other end of the line here. So we'll end up over here. And that would be our carbon number 1. So in this case, we will actually have 2 groups that will be off of the ring because of the way this thing closes as a ketone in this case. Yeah. Obviously, if we were to draw the beta, it would look exactly the same, except the last one would just be flipped. So the OH would go up and the carbon group would go down. So they will stay on the opposite sides of each other. Question on that one there. Question on how to bring them into a ring structure. Question?
On carbon 2 was beta, it would be up, and then the alcohol would be down.
Yeah, so if you're asking if we were to draw the beta one, it would look identical to this. So we would still have this guy over here, and then we have this one up. This one would go down. And now if this was beta, because it's beta, that means that OH group has to go up. And because in this case, that other carbon is attached to it, basically, it's got to go down. Yeah, that would be obviously our beta version here. And this would be our alpha version in this case. And again, it really refers to the OH positioning. And it just happens in this case because that last carbon is not part of the ring. Is sort of dependent on where that OH ends as to where it will end up or down that last carbon. Other questions on that there? All right, so let's say we had a fun with rings today. Let's say we had a cyclic structure, say like I don't know, we'll go with Let me just make one up and see how bad this is going to turn out. Let's see here. There we go. Let's say we have this guy right here. We'll go that way. We'll go that way. Why not? We'll go up. And eeny, meeny, miny, mo, we'll go up. Why not? All right, let's say we wanted to take this guy out of the cyclic structure and return it back to the open structure, right? Can we do that? Probably. So let's say that we wanted to do this, and let's say we wanted to draw our friend the L isomer of it, right? All right, so where should we start on this? Well, we definitely shouldn't just go to the next problem. We should probably look at this problem and figure it out. So we want to start with really how many carbons we got going on, right? So if we look at this here, I know I got a carbon there. That's 1, that's 2, that's 3, that's 4, that's 5, and that is 6 carbons. So I know right off the bat when I open this thing up, I need 6 carbons. So I know this guy at the end is going to be carbon number 6, right? So that's pretty easy because that guy always ends up left off the ring. Now, what I also need to figure out is what type of functional group I got going on here. What type of functional group do you think I should put there? I would go with an aldehyde, and the reason I would go with an aldehyde is if we look at the one we just did, which is a ketone, right? Or ketose, we have not one carbon group off of the chain, but we have 2, which means when we look at our ring structure, A, it's a smaller ring, right? And B, there's another carbon group hanging off of it at the end there by carbon number 1, which clearly we don't see here. There's no other carbon group hanging off over there by carbon number 1. So you are probably pretty safe to assume that this is going to be our aldehyde group, right? Which obviously in this case would be carbon number 1. And now we can kind of fill in the rest of them. That's going to be 2 carbons, 3 carbons, 4 carbons, 5 carbons, and our 6th one that's sitting down there. Any questions on that so far? So we can number them if it helps you. That is 2, that is 3, that is bad math, that is 1, and missed the carbon there. It's kind of right. I'll try that again. That's 1, 2. Try that again. 1, 2, 3. There it is. 4 and 5, and then 6 carbons. So now we're just going to work our way backwards. We know on our ring that that's carbon 6, that's carbon 5, that's carbon 4, that's carbon 3, that's carbon 2, and that is carbon number 1. So we are going to start with obviously not carbon number 1 because we already got that sort of situated, right? So might as well go to carbon number 2. And here my OH group is up, which means originally if it's up, it was on the left or the right-hand side. It'd be on the left-hand side, right? Because when it falls over, it's got to go up, right? So because my OH group is up here, that means it originally started on the left. So at carbon number 2, that is where I'm going to put my OH group. When I go to carbon number 3, I again see my OH group is up, which means it originally started on the left-hand side. So we will put it over there as well. Now, when I go to my carbon number 4, my OH group is down. And remember, when it drops, that means it has to be on the right-hand side. So since this guy is down, that's going to, excuse me, it's going to be a right. So that is where I put my OH group. Any questions so far? Yeah. I got 1 to go, which is that carbon number 5 there where we kind of made the ring. So I'm undoing it. And it says what letter there I want to draw? And L means left or right? Left. So we might as well put the OH group there on the left. Seems like a good idea. There we go. Now I just opened that ring free of charge. There we go. Any questions on that one there? All right, so why don't you try one? Why not? Let's try. Actually, let's do let's do And for fun, I know it's not fun, but let's try it anyway. Let's do this one too. And let's do the D on that one. And let's do an F. Okay, let's take a look, see how you're doing. So they both look very similar, but they are quite different in terms of when you open them up, hopefully. So we'll start with sort of the same approach, which is maybe figure out how many carbons we should end up with. We'll do the guy on the left here. So that's definitely 1 carbon there. That's 2 carbons, 3 carbons, 4 carbons, and actually only 5 carbons actually in this case. So a little pentose action happening. We know obviously that last guy is going to end up on the bottom there away from our functional group. So in this case, this would actually be carbon number 5 in our diagram here. We also, when we look over here at the end of our ring, don't see any more carbons happening, which means that our functional group should be at the end there. And if it's at the end, it's got to probably be the aldehyde group at the end there. And that would be our carbon number 1. So now we know that's 5, that's 4, 3, 2, and 1 in this case. So we'll just fill in the rest of them. So that's 1, 2, 3, 4, and 5 in this case. Once again, here we'll start not with carbon number 1, obviously, since we already situated that. So we're going to go to carbon number 2, and we see our OH group is down, which means it had to be on the right to start with when he dropped it on its side. So that would be there, and that H would be there. We go to carbon number 3, OH group is also down, so we're going to get an OH there and an H there. And in this case, we're drawing the D, which means my last OH should end up at the right-hand side as well in this made-up example here. And that is our last chirocarbon in this particular case. Any questions on how we open that thing back up? Yeah. All right, so now we're going to do the same thing with the guy on the right. We're going to count carbons. So that's 1 carbon there. That is 2 carbons, 3 carbons, 4 carbons, 5 carbons, and once again, 6 carbons in this case, as we got that guy that is off the ring as well. So in this case, we once again will have that group at the bottom there, this carbon number 6. We also do see a carbon there at carbon number 1, which is off of the chain, which means that's going to be at the top here in this case. That also should tell us that this is actually a ketone, right? Because we don't have the carbon-oxygen double bond happening. So our next carbon there would be our carbon-oxygen double bond there. So that's carbon number 1, carbon number 2, that would be carbon number 3, carbon number 4, carbon number 5, and now our carbon number 6. So we're almost there. We can number this to give us some orientation: 6, 5, 4, 3, 2, and 1. So we've already taken care of 1. We've already taken care of 6. We're going to go to carbon number 2. I'm sorry, carbon number 3, I'm sorry. And carbon number 3 is up, which means it originally was on the left to do that. So that would be carbon number 3 there. Then we go to carbon number 4, where our OH is down, which means it was on the right there. And our last one, where really carbon number 5 and carbon number 2 come together basically to make that ring, which is this part of the ring that comes together basically. We're going to go L in this case, which means we're going to throw that last OH there on the left. Yeah. Question on that. So even though they kind of look very similar, it's actually one's an aldose and one's a ketose. And again, you want to look for those little things if you happen to need to open it up. Any questions on drawing them in cyclic structures, opening them up? Maybe something you need to do for the final, I would imagine, maybe. Question will be like right there. Do it and make sure you do it. Yes. Any questions on that there? All right. Fun withdrawing today. It's good. Good times. All right. So we kind of went through this. This is again another example. And again, the steps that we followed, we basically took it and dropped it on its side. We then basically take that last chirocarbon, which in the case of a hexose would be carbon number 5, and we're going to bring it to the carbon oxygen double bond, and that again is going to close up our ring. And if we counted our carbons in that case, like we did on those examples, we would end up here with our 5-member ring. And again, the last one, either the alpha or the beta, will determine where that last OH will end up. And obviously, if we had something like we did with that ketose, then that carbon group on the end there would go one way or the other, depending on sort of where the OH group ended. Any questions on any of that stuff there? Yeah. So glucose will sort of open up and close up, and just show you how the oxygen and all that gets incorporated into the ring. When our carbon number 5 here goes and attacks our carbon number 1, we make a cyclic hemiacetal. So if you remember, the hemiacetal is our carbon with the hydrogen and our OH group, right, attached to it. And what happens here, as you can see, is there's actually a shift that occurs. This hydrogen actually ends up over here with the double bonded oxygen, and that is sort of where our OH group ends up with. And this oxygen kind of stays there and gets incorporated into the ring. So that is where we kind of skip over the 5 in this case and the 1, because that's what's happening with those two as they come together to close the ring. The oxygen from the OH group on carbon number 5 there basically gets incorporated, and there's like a hydrogen shift that shifts over to the other oxygen on carbon number 1 and makes an OH group there, which obviously will be either alpha or beta where it will end up, but it will end up in one of those positions. So in case you were curious, that's basically how the oxygen sort of gets incorporated into that ring, and why we sort of skip those two as we're kind of counting up and down, because basically they come together and sort of close up the ring on this end of it, and that's where we end up with that oxygen that sort of binds the two together. Obviously, when it opens, it pretty much does the opposite. The hydrogen goes back and it kind of splits back open into the open form. And in terms of alpha D-glucose or our beta D-glucose, it does kind of open and close a lot. The majority of the time, though, it is staying in sort of the beta configuration. Kind of the rest of the time there, it's going to be in the alpha configuration. And again, we see basically we're going to have this guy slide over, and this guy's going to incorporate there into the ring, and we'll have that oxygen that happens in that case. So fructose is the one we just sort of did, or very similar to the one we did again with our ketone here. We are going to take that last chirocarbon, but once again, it's got to always end up, and that's just what you should remember, is it will always end up at the carbon oxygen double bond to close it. And once again, at that point, we could just count our carbons. And here we do have 4 carbons, which is why we took the 1, 2, 3, and 4-member ring like we kind of did on that other example, which is similar, and closed it up in that particular case. So when it helps you to do that is to draw the arrow, and again, just circle the carbons, and that will point you to the right ring. And that's where you want to start with in terms of your drawing. All right. So I think we did a number of these examples. So again, we would do the same thing in this case. We would go here to here, tells us 1, 2, 3, 4, and 5-member ring, which again is that cyclohexane type looking ring. And again, we would put our carbon number 6 up there on top and then start numbering. And now we could again just place our things as this is carbon 1, 2, 3, 4, 5, and 6. Here, starting at carbon number 4, my OH group's to the left, which means it should go up, right? Left means up and right means down, basically. Carbon number 3, OH group is to the left, which means it should go up. OH group at carbon number 2 is right, which means it should end up down. And here, alpha means that my final OH group again should end up on the downward cycle. So again, if you get comfortable with that, left, right is up, down, you don't even have to redraw it. You could just go, okay, that's on the left, it should go up, and that's on the right, it should go down. And you could just do it from how it looks from the original structure. Any questions on that there? All right.
Hopefully it looks like what I drew. That's good.
All right. So let's talk a little bit about some of the properties here of monosaccharides, which we've been talking about. Monosaccharides are reducing sugars. Reducing sugars are pretty much any monosaccharide that has a carbonyl group and that oxidizes to a carboxylic acid. We pretty much undergo our positive test with our Benedict's reagent. If you remember, we used our Benedict's reagent, right, to go from aldehyde to carboxylic acid, right? It turns from that bluish color to that gross looking orangey red mess when it's positive. So most sugars are going to be reducing sugars. All the monosaccharides there, glucose, galactose, and fructose will undergo this sort of reaction. And here, as you can see, it's basically the same oxidation as we talked about in organic chemistry. We're going to go really from an aldehyde to a carboxylic acid, and we're just going to insert basically the O or the oxygen in there. Everything else will basically remain the same in this case. And we're not going to worry about that, I think. All right. Not going to worry about that either. All right, so let's talk a little bit about disaccharides. Disaccharides are basically two monosaccharides that have been put together, and disaccharides basically come together by removing water. So we remove water, and then they join up together, and they make a certain type of bond, which is referred to as a glycosidic bond. And there's a few different types of disaccharides that are common here. I'm assuming with cheese, as I see there, and dairy. So if we take two glucoses units and really bind them together by removing water, we will get what is known as maltose, which is a disaccharide. If we take a glucose unit and a galactose unit and put them together, once again, by removing water and joining them together, we will get lactose. And if we have glucose and a fructose together, we will get sucrose, which is basically just sugar. You need to know this slide pretty much, yes. You need to know the different disaccharides and the monosaccharides that make them up. Yeah, we're gonna go through each of these here right now, but it's a good slide that has it all together. You need to know that maltose is made up of two glucose molecules. Lactose is a glucose and a galactose. Sucrose is a glucose and a fructose molecule. So let's take a look at each of these here. We'll start with maltose. Maltose is known as malt sugar. It's a disaccharide. And again, it's made up of two glucose molecules that are together. It's obtained from the hydrolysis of starch. And it's linked together by a special bond, which is known as the alpha 1,4 glycosidic bond. So you should know that bond and you should recognize it. And we're going to take a look at it here in just a second. But it's linked together. That is the bond that basically links together the two glucose units. So when they come together, that is how that bond is linked. And is what is referred to as an alpha 1,4 glycosidic bond. This is the sugar that are used in cereals, candies, and brewing of alcohol. So let's take a look at that bond so we can kind of see what that means here instead of just looking at the names. So these are two glucose molecules that are on top. And if we were to number the ring here, like we just did when we were drawing those things, that would be carbon 6, carbon 5, carbon 4, carbon 3, carbon 2, and carbon number 1 right there. Same thing on this guy, that would be carbon 6, carbon 5, carbon 4 right there, carbon 3, carbon 2, and carbon 1. The glucose molecules here, they're alpha, right? Because that carbon number 1 OH group is pointing down, right? So this is alpha. So what happens when these two come together is we're going to remove water out of those two. So if you just think about water, which is H2O, you get rid of two H's and one oxygen, which leaves you one oxygen left. Yes, and that one oxygen is the linkage point that we are talking about here with our alpha 1,4 glycosidic bond. It is removing the water, and those two glucose molecules are going to be joined by the oxygen. That is our alpha 1,4 glycosidic bond. So how do we get the name? It is named like this. The glucose on the left, that is carbon number 1, which is why it's 1. The glucose on the right is hooked in at carbon number 4. That is the 1 and 4 part of the name. And the alpha part is, it's an alpha, yeah. It's the OH group there was an alpha originally. And we know alpha is down. So how you could very easily recognize it as an alpha, say 1,4 glycosidic bond is, if you look at that bond, it's kind of going down, yeah, how it's kind of joined. And that's because that OH group was originally down as well. So if you see that sort of connection where it kind of looks like it's going down to the O, that's definitely what the alpha sort of linkage looks like in this case. So to put them together, we would have to remove water from the two of them. And if we wanted to break it apart, we would have to just throw water back in and they would break back apart and you would get the two OHs going in the opposite direction. So if you want to take this disaccharide back to the monosaccharides, we would just add the water back in and they would basically separate right where they link. And obviously each would get their appropriate OH group in that particular case. Question on that bond there. So let's take a look at then what's going on in lactose. Lactose is a disaccharide that's made up of a beta D-galactose and an alpha or beta D-glucose. It contains actually a different glycosidic bond as to how it comes together. It is still going to come together by removing water, but the way it comes together is a little bit different. This obviously is the bond that we find in, or this is what we find in milk products, and also why people are lactose intolerant. They have problem breaking that bond there, perhaps to hydrolyze that in your body. And when we look at our glucose and our galactose molecule, this is carbon 6, this is carbon 5, carbon 4, carbon 5, carbon 4, carbon 3, carbon 2, and carbon 1. I'll get that whole counting thing eventually. That's carbon 6 on this guy. That's carbon 5. That is carbon 4, 3, 2, and 1. So they are going to come together through carbon number 1 and carbon number 4 on the respective molecules there, which is why the name here is beta 1,4 glycosidic bond, because again, it's carbon number 1 and carbon number 4 coming together. And this is a beta OH, which means we will actually get a beta connection. And you can see that is this connection right here. Unlike the alpha one, you could kind of almost picture it going upwards, right? And that is what beta is, up. So if you see a bond that connects those two sugars going kind of in that upwards position, that's going to probably be a beta connection, as opposed to what we saw with the alpha, where it kind of looks like it's coming down, right? And that's what alpha means, which is down. And that's a good way to sort of remember, if you have the picture drawn to you and maybe asked to identify the type of bond, that you can look at it and see sort of what's going on. The numbering really just comes from the carbons that are involved when they are put together. So that you just want to start at the top left and number counterclockwise as to how many carbons, and you'll be able to figure out really the numbering that goes with it and stuff like that. So once again, water goes out. We leave one oxygen as sort of the connection point between the two. And just like previous one, if I wanted to break that back down, I'm going to just throw the water back in and it will break it apart at the same spot there. Question on that there. So that's a beta 1,4 glycosidic bond, which is the bond that we find in lactose. And our last disaccharide there, which is sucrose. Sucrose is table sugar, and it is obtained from a glucose and a fructose molecule. And it also has a different glycosidic bond. Dare I say that this is a alpha beta 1,2 glycosidic bond. Like, I'll ask, anybody remember alpha beta, the supermarket? Yeah, good. I'm not that old yet. That's good still. So yeah. There used to be alpha beta. I think it became like food for less, I think, and then it became Ralph's. I think owns them all now, pretty much. But used to be a supermarket called Alpha Beta. So here we have actually an alpha beta 1,2 glycosidic bond. So let's take a look as to why it is named that way. If I sort of redraw these things kind of quickly here, we'll do this here, and we got a little bit of this. And in this case here, we'll just look at this here. We have our OH and our OH kind of coming this way. So in this particular case, the numbering is that's going to be 6, 5, 4, 3, and 2. If I need that right there, I feel like I'm missing somebody. 6, 5. I am. I feel like I misdrew a carbon there. I lost a carbon somewhere along the way. I put my group in the wrong spot. That's bad. All right, I'm gonna try that again. Let's put that in the right spot there. That might be a little bit better, and then I can number right. There you go. I so quickly drew it, I forgot where my carbon went. All right, so let's try that again. There we go. This right here is where that group should end up, and that's going to be carbon 6. That's carbon 5. That's carbon 4, carbon 3, carbon 2, and carbon 1. That looks a little better. That's going to be our carbon 6, 5, 4, 3, 2, and obviously our 1 is off of the chain here. So what's going to come together in this case is these two guys here. And in this case, it's actually both at the end, which means we do need to incorporate both the alpha and the beta part of it. That is alpha, which is going down here. And then we have our beta guy that's going up. We don't have to do that on the previous ones because we were connecting over there at carbon number 4, which is not an alpha beta position. So here, because they're both really at the alpha beta position of each of these sugars, we do have to include that. So that's going to give us our alpha beta. And once again, it is carbon number 1 and carbon number 2 that are coming together to make that. And we are going to remove our water like normal, which means we will end up with, again, that 1 oxygen that's going to tie it together. That is right there. So sucrose, which is our table sugar, held together by a alpha beta 1,2 glycosidic bond. And this one you could kind of tell is also looks different than the previous two that we saw. We kind of had our alpha only bond that looks like it's going down. We had kind of our beta only bond that looks like it's going up. And the combo of the two looks like it's going straight up. Yeah, so guys, the alpha and the beta. And it's also both on the right-hand side of the molecules here, right? The other one was the right-hand side of one, the left-hand side of the other. So if we look at this one, right-hand side of one, left-hand side of the other, and the previous one was the same. But here, the connection's happening on the right-hand side of both of those guys, again, where you have the alpha or the beta positioning. So that's why it kind of goes straight up rather than either this way or down to it. Question on that. So once again, you do need to know each of these guys. And obviously you don't have to draw any of the guy breaking or anything like that. But again, if we wanted to break this bond, we would just add our water back in. And once again, everybody would get their OH group back on each side of it here. All right, so let's talk a little bit about this here. So for each of these here, lactose is made up of what things? Galactose and a glucose, perhaps. Yes, sounds good. Maltose is made up of a couple of glucoses, I hope. And that sucrose was the last one we were looking at there. That was our fructose and our glucose. Right. There we go. Okay. So once again, you do need to know each of those disaccharides, the monosaccharides that make them up, and you do need to be able to identify the glycosidic bond, either just to know what it is or again, if that glycosidic bond is drawn for you in a molecule, be able to identify the type of bond that is happening there as like an alpha 1,4, beta 1,4, whatever it may be, something like that. Any questions on that there? Yeah. So let's talk a little bit about polysaccharides. Some potatoes. Sounds good. So polysaccharides are really polymers of glucose molecules. So polymers are long-chained things that are put together in repeatable units. So our repeatable unit here is glucose. They're pretty much all put together by just taking out water and connecting them through some type of glycosidic bond like we were just looking at, either an alpha 1,4 or maybe some other type of bonds happening there. They include amylose and amylopectin. These are starches that are made of alpha D-glucose. They also include glycogen, which is made also of D-glucose, and cellulose, which is plants and wood. Made by beta D-glucose in this case. So that's our glucose molecule, and basically a bunch of those together will make each of these things, these polysaccharides. So let's start with our potatoes here. We have amylose and amylopectin, and down here is our we have our amylose, which has a bunch of glucose bonds together, all by taking out water. So water coming out of each of those guys and putting them together. Again, if we look at this picture here, it is going like this, which means that should be a alpha bond, right? That's what it looked like previously. So these are all connected through an alpha 1,4 glycosidic bond like we saw previously. And again, it is basically, if I draw it correctly this time here, our 1 there to our 4th carbon on the other guy. And that is the connection that we have on all of those. What makes this different than amylopectin is it is unbranched. So it's just a long straight chain of glucose after glucose, all put together by taking out water. And that's different than amylopectin, which is also a really long chain of glucoses together. It also has the same glycosidic bond at carbon number 1 to carbon number 4. But the difference here is every so often there is a branching point that happens. So it's a little bit more branched than the first one, which has no branches, it's just straight. So you got some branch work happening here. And it also has an alpha, as you can see here, 1,6 glycosidic bond. And it has a 1,6 glycosidic bond, as you can see here, because it is connected to the alpha carbon there. And it is actually connected in this case to carbon number 6, that carbon that's above the ring here. So that's why there's no 2 letters there, alpha or beta. It's just alpha because the only alpha or beta carbon comes from here. This is this carbon number 6 where the connection happens, and that gives us our alpha 1,6. So it looks very much like our alpha beta one that we just saw. But again, it is not connected over here. It's actually connected to carbon number 6. So that's why it's only the alpha 1,6 bond and not like the alpha beta 1,2 bond that we saw previously in this case. So these two are very similar. They're all just glucose units together. One is unbranched. One has some branching that is happening here and a couple of different sort of bonds that are happening. So amylose, as we see there, is a continuous unbranched chain of our glucose molecules, again with that 1,4 bond, that alpha 1,4, and again alpha as it's coming down here bond between them that holds them together. Clearly, if you wanted to break that apart, you just dump a bunch of water in there and hope for the best, and that will help break them apart. Amylopectin again has the same deal, except as we just saw there, there's some branching that happens. And again, a 1 to 6 connection, as it's also a 1 to 4 connection, which is our alpha connection, and our alpha 1,6 that is happening in this case at the branch points. question on those there? That then brings us to glycogen, which is, where we store our energy, right, as glycogen. So we could break it back down through gluconeogenesis, right, and use it for energy. And I don't remember anything else besides that, but I know that sounded familiar. But glycogen is a polysaccharide of your stored glucose molecules. It is very similar to amylopectin, except it has a bunch of branches happening there. So not just one every so often. It's very highly branched out, and it has basically the same sort of connections that occurs there. So glycogen, very similar to amylopectin, but a lot more branching happening. And again, we basically store excess glucose and stuff like that in our muscles so that we can then break it back down and use it for energy when you need it as sort of stored energy. Cellulose is a different sort of connection that occurs because it involves a beta glucose. It is a polysaccharide and unbranched, but it has a beta 1,4 glycosidic bond. And again, that's because it comes from a beta glucose, which means the OH group is up. So once again, if we look at this connection, we could kind of see that upwards connection like we talked about and saw previously, which is our beta connection that's happening. And again, it is carbon number 1 of this guy and is carbon number 4 here. And this original carbon had the OH group up, which is why it's beta and why it looks like that, like it's going in the upwards direction. Once again, we don't use any alpha or beta for carbon number 4. It's only reserved for pretty much the end carbon. And since the connection is not there, obviously at both parts, we just call this the beta 1,4. So this is a unbranched chain of beta 1,4 glycosidic bonds. It cannot be digested by humans, so you probably shouldn't eat that there. I hope you don't do that because you won't be able to break that apart. Let's take a look at each of these here, identify the polysaccharides and the type of glycosidic bonds that are happening here. And for each of those there, we have our cellulose, which has our beta 1,4, our amylose, which is alpha 1,4, amylopectin, which has the alpha 1,4 and the alpha 1,6, and our glycogen, which also has the same thing as amylopectin. The difference is much more highly branched there with our glycogen in this case. Any questions on that there? So for this, you do need to know amylose, amylopectin, cellulose, and glycogen. You do need to know sort of the difference between them, which ones are branched, which ones are unbranched, which ones are highly branched. Again, the connections in general, you need to be able to recognize perhaps a glycosidic bond. Again, if it maybe is drawn for you, you can identify what type of glycosidic bonds happening there or be able to identify it. Any questions on that? So that wraps up carbohydrates. Yeah. So thank you from the carbohydrate chapter. What you do need to know, obviously, is you need to know stuff like chiral, achiral, being able to identify chiral carbons. Obviously, those carbohydrates that I said star on that page, to be able to recognize structures like glucose, fructose, the actual structures. You won't be asked to draw it, but be able to recognize it. Obviously, I'm assuming to be able to draw it into a ring form or out of a ring form would be something that would be good to know. Here again, you need to understand and be able to recognize the glycosidic bonds if they're drawn for you, and obviously the difference between these things here. Any questions on any of that stuff there? All right.